Carbon fiber reinforced polymers, or CFRPs, are the structural backbone of modern aerospace design. But in orbit, they face a persistent threat: micrometeoroid impacts. Traveling at several kilometers per second, these small dust grains strike the CFRP matrix, causing localized stress fractures to splinter outward. Once a microcrack forms, the extreme temperature swings of space take over. Moving from hundreds of degrees above zero in direct sunlight to hundreds below zero in orbital shadow causes the material to rapidly expand and contract. This thermal cycling drives the initial microscopic stress fractures deeper, forcing cracks to propagate through the structural matrix. Addressing this damage requires external repair methodologies, like patching or applying localized resins. However, introducing secondary materials creates inconsistencies that compromise the uniform structural integrity of the original composite. As mission profiles push further outward into deep space operational environments, relying on human intervention or Earth-based supply missions for structural maintenance becomes logistically impossible. To ensure long-term structural longevity, engineers are adopting a biomimetic approach. They are developing synthetic materials that replicate a biological healing process, capable of autonomously detecting and arresting mechanical failure before it leads to a catastrophic breach. The field of self-healing materials bridges biology and synthetic chemistry. Much like how human blood clots and hardens to seal a physical wound, these materials are designed to respond to localized damage at the polymer level. Two dominant frameworks exist. First is the extrinsic paradigm. The host structural matrix remains static, relying entirely on embedded physical reservoirs of reactive chemicals. Conversely, the intrinsic approach builds the healing mechanism into the polymer network, using dynamically reversible covalent bonds that break and reform. Each framework forces a strict engineering compromise. Designers must balance three factors: the maximum recoverable mechanical load, how many repairs are possible, and the specific activation energy. Because these mechanisms require vastly different manufacturing processes, the selection between extrinsic and intrinsic chemistry dictates the ultimate operational life cycle of any deep space infrastructure. In an extrinsic matrix, the bulk polymer, usually an epoxy resin, provides the structural rigidity. It lacks any inherent chemical reversibility, acting purely as a static host structure. During manufacturing, engineers co-distribute thousands of discrete microscopic capsules throughout this epoxy host. These microcapsules are sealed with a liquid monomer, commonly dicyclopentadiene or DCPD, image itself. As a fracture moves through the brittle epoxy matrix, it intersects these capsules, physically tearing their outer shell walls. Once ruptured, the DCPD monomer is immediately drawn into the empty void of the fracture plane, driven entirely by fluid capillary action. To solidify, this monomer must encounter a second component. Dispersed alongside the capsules in the host matrix is a ruthenium-based Grubbs catalyst. When the flowing DCPD contacts this catalyst, a rapid chemical reaction begins. This triggers a ring-opening metathesis polymerization, or ROMP. The cyclic olefins in the DCPD monomer transform into a dense linear polymer, which permanently cross-links the two fractured surfaces. Because the resulting ROMP polymer is highly durable, this extrinsic method yields exceptional mechanical recovery. It can restore up to 90% of the material's original fracture toughness, making it highly suitable for rigid, load-bearing aerospace composites. The strict limitation of discrete microcapsules is their finite volume. Once the local reservoir ruptures and polymerizes, the healing agent is exhausted. If a second crack propagates through that exact same coordinate, the matrix possesses no further capacity to heal it. For orbital structures subjected to continuous cyclic damage, a single-use repair mechanism is insufficient. This three-dimensional isometric view shows how structural engineers replaced discrete spherical capsules with interconnected microvascular networks. This allows healing agents to be continuously routed from larger external reservoirs directly to any localized fracture, bypassing the volume depletion problem. These networks are fabricated by utilizing robotic 3D printing to deposit fugitive inks, a mixture of high and low molecular weight hydrocarbons, into a specific scaffold shape. After the epoxy resin cures around the scaffold, the ink is evacuated using heat and a light vacuum, leaving behind a precise network of hollow channels. Operating this topology introduces severe fluid dynamic constraints. Engineers must maintain precise liquid viscosity so the agents can flow through microscopic capillaries, while also ensuring accurate stoichiometric mixing of two-part adhesives once they reach the fracture site. While microvascular networks eliminate the single-use limitation of capsules, the complexity of pumping and mixing two-part fluids across a vast capillary grid introduces major mechanical vulnerabilities to the structural design. The intrinsic healing paradigm avoids fluid dynamic problems entirely and demonstrates how this is accomplished by engineering the polymer network with reversible covalent bonds. It relies on a reaction where a diene and a dienophile combine to form a specific ring structure. Unlike standard irreversible epoxy, this bond is dynamically sensitive to heat. By applying sufficient thermal energy, a retroreaction occurs, causing the covalent bonds to temporarily dissociate. This dictates a strict activation energy requirement. To mobilize the polymer chains for repair, the material must be heated above its specific glass transition temperature. While held in this mobilized, elevated temperature state, the polymer chains gain sufficient kinetic energy to physically interdiffuse across the crack boundary, closing the microscopic gap. As the thermal energy is removed and the temperature drops back below the glass transition threshold, the diene and dienophile molecules rapidly rebond, locking the matrix back into a solid state. Because this specific cycloaddition chemistry is native to the polymer backbone itself, no physical material is lost or consumed. This thermal cycle can be repeated infinitely at the exact same fracture site. Intrinsic dynamic bonding offers the immense advantage of infinite repeatability, but it is severely constrained by its activation barrier. The repair cannot occur autonomously at ambient space temperatures. It demands a targeted, high-energy thermal stimulus. This cross-section of NASA's LAR-TOPS 122 architecture shows a highly specialized application optimized for high-velocity ballistic micrometeoroid mitigation. To deploy theoretical paradigms in active spaceflight, aerospace agencies engineer targeted solutions to circumvent their limitations. The LAR-TOPS 122 architecture utilizes a tri-layer design. Rather than relying on an external heating element, it harnesses the extreme friction heat generated by the projectile impact itself to trigger localized polymer melt elasticity in the solid front and back layers, causing the puncture hole to rapidly snap back and close. This is immediately followed by a secondary extrinsic mechanism. Sandwiched in the middle layer is a viscous reactive liquid monomer. This fluid flows into the remaining void and instantly solidifies upon exposure to ambient atomic oxygen. Conversely, the European Space Agency's Project Cassandra focuses on composite structural longevity, testing a material known as HealTech. HealTech relies on an intrinsic-style resin reflow. To repair fatigue damage and microcracking, it requires a significant amount of localized thermal activation. This carbon fiber panel overlay illustrates ESA's solution for providing that heat without manual intervention. Engineers embedded a network of optical fiber sensors directly into the composite. These sensors continuously monitor structural health and autonomously isolate the exact physical coordinates of a fracture. Once damage is detected, embedded 3D printed aluminum grids are activated at that specific node. They autonomously heat the isolated zone to between 100 and 140 degrees Celsius, triggering the required resin reflow and repairing the material. These applied engineering models successfully circumvent the theoretical constraints of both intrinsic and extrinsic chemistry by hybridizing them with targeted mechanical and thermal triggers. Extrinsic, capsule-based systems provide the most robust structural healing for discrete, high-velocity impact events where immediate, load-bearing cross-linking is critical. Meanwhile, intrinsic dynamic bonding provides the only viable, infinitely repeatable repair mechanism for managing continuous mechanical fatigue and extreme thermal cycling. Because these operational hazards vary wildly across a single spacecraft, the architecture of future reusable space transportation will require the abandonment of uniform, monolithic material solutions. To see how this manifests, we can look at the schematic of a next-generation launch vehicle. The exterior hull utilizes hybrid reactive multilayers, optimized with extrinsic chemistry for immediate ballistic micrometeoroid shielding. Conversely, the internal cryogenic propellant tanks, subjected to extreme thermal contraction and pressurization cycles, use intrinsic matrices that can be repeatedly thermally activated to heal cyclic fatigue. By precisely matching synthetic reactive chemistry to the specific damage profile of each operational zone, Aerospace engineering erases the traditional life cycle limits of deep space infrastructure.